Okay. A long time ago, I taught you about the relationship between length, area, and volume. And I will remind you about it now. Here was the deal. You know what? I need a little bit more space. No, I'm going to have to deal with it. Got no choice. Here was the situation, you guys. Tell me if this sounds familiar. We would always do three things, all in a row. Length, area, and volume. Okay? I always do all three. And now, here's what we would decide. We would always start with length if we could. Let's see. The size of a sphere increases so that the diameter doubles. Diameter doubles, that's the length, right? So I'm talking about the length doubles. Let's just call it x. If the original length was x, if I double it, what's the new length? 2x. The new length would be 2x. Okay, so I've got that so far. That's the length doubling. Now, if I have a length, the area is always going to be the length squared. Okay, that's why the original area was just x squared. Now, when I do the new area, I have to use my new length. So my new length is 2x. So if I want to find my new area, I have to take that 2x and square it. Okay? Now if I square 2x, that's like 2x times 2x. What am I going to get? I'm going to get 4x squared. Now look how the original area, x squared, compares to the new area, 4x squared. How many times did I multiply it? Just look at the number in the front. Right. The new area is 4 times as big as the original area was. Okay? It's 4 times as big. Let's just do all three. The volume. The original volume is always the length cubed, so x squared. The new volume is going to be the new length cubed. So notice I'm still going back to the 2x. It all goes back to the length. So, but I'm going to take my 2x and I'm going to cube it because I'm doing volume now. What's 2 cubed? 2 cubed is 8. So this is going to make 8x to the third power. So the length doubled. The area was multiplied by 4 times as big. And the volume is multiplied by 8 times as big. So that's what you would say is... So the answer to this question comes from the second one. What happens to the surface area? It's multiplied by 4. Or you could say it's 4 times as big. You could say it that way too. Oh, and then I guess I already answered part B. What happens to the volume? It is, right, I can say multiplied by 8. I'll word it the other way this time, just so you see it both ways. I could say it is 8 times as big. Okay, that was key. Did you understand that? I feel like we need more practice. It's going to show up in other problems. Okay. So here's a slightly more complicated version of the same thing. It has just one extra step to it. Are you ready? Okay. The volume of a large ball is 810 cubic centimeters. The volume of a small ball is 30. Let's see if I have space. Okay, so we have a small ball, and then we have a large ball. Okay? The small ball, 30. The large ball is 810. Now that's volume. That's volume. Okay? Now here's the key question. I need to know how many times the volume was multiplied. I need to know the multiplier. What calculation will I do to find out how many times bigger the bigger volume is? I'm going to divide it. You are good. I'm going to divide it to find how many times bigger it is. So take your calculator and do 810 divided by 30. That'll tell me how many multipliers. 27. Okay? So that means, think about it. 30 times 27 would give me 810. So the bigger ball, the volume, is 27 times bigger. Okay? So let's set up our calculations. All right, so we know the volume is that much bigger. So here's our thought process. I'm going to do this off to the side. Let me make sure you can see it. We always do length, area, and volume. Okay? This time we know volume first. The volume is multiplied by 27. So as I set up my little pattern here, x to the third power is the original volume. It became 27 x to the third power. The volume was multiplied by 27. Now, let's work backwards and get to what happened to the length. Okay, this is the key to everything. If the volume is multiplied by 27, and we know that the volume would come from cubing the length, what number must the length have been multiplied by? It must have been 3, okay? Because, Mr. Perez, think third power. Think third power. If the length was multiplied by 3, if I take 3 and I cube it, because I'd have to do the third power to get to the volume, 3 cubed is 27. So that tells us that the length must have been multiplied by 3. What about the area? Okay, x squared. Now, it's based off of the, yes, it's based off of the length again. If the length is multiplied by 3, we would have to square it to get the new area. So the new area must have been 9. Okay? So that's how you had to do it. We started with the 27. That was volume, so we had to think backwards. We had to ask ourselves, what to the third power would make 27? We decided that was 3. 3 to the third power. It had to be a 3 here. Once we have the 3, to get area, we square it. So it must be 9. So now I'm ready to answer all the questions. So the question is, how does the radius of the large ball compare to the radius of the small ball? Radius. Is that a length, area, or volume? Radius. That's a length. So the length is how many times bigger?
3.
It's 3 times bigger. So just put, it's 3 times bigger. Okay, how does the radius of the large ball compare to the small ball? It's 3 times bigger. How does the diameter of the large ball compare to the small ball? Burton, what do you think? It's still 3 times bigger. Because diameter, remember, diameter, the distance right across the middle, that's still a length. Still a length. So it's still 3 times bigger. Okay, radius and diameter are both length. All right, now how does the surface area compare? That's 9 times bigger. Looking back at our analysis, the area is multiplied by 9. So surface area would be 9 times bigger. Okay, that's how you do that. All right, look back at problem number 3. The mass of a ball is 2,500 grams. And look, I've got a formula right there. If the radius of the ball is 5 centimeters, calculate the density. Okay, so I gave you this little formula for density. You don't have to memorize this. They would give you this in the problem. Okay? So density is mass divided by volume. Do I know either one of these things right now? All right, I know the mass because it gave it to me. What was it? 2,500. Okay, now I need to know the volume. Is that 5? Do I just put a 5 down here? No, that's just the radius. How do I find the volume? Well, the formula for the volume of a cube is given to us. Okay? That will be provided for you. Okay? The volume of a cube is 4/3 pi times the radius cubed. 4/3 pi r cubed. Okay, that's the volume of a sphere. So this giant expression is will give me the density, mass over volume. So you know what? I'm just going to type this entire thing into my calculator because the TI-30 is a wonderful thing. I might need you to help me remember what the numbers were. Are you ready to help me? Okay, what was in the numerator? Okay, what was in the denominator? Good man. All right, was everybody able to type this in your calculator? Do you know, okay, how to do it so it gets in there? Okay, so 4.77. That's it. That's the density. That's how you do it. Okay, let's do number 4. This time we're going to leave our answers in terms of pi. Look, if a ball rolls under a fence that's 12 centimeters off the ground, I'm indirectly giving you some dimension of the ball. Imagine that the ball just barely fits through this 12-inch gap. Is that giving me the radius, the circumference? What? What's that giving me? That's giving me the diameter, right? If this is the gap and the ball just barely fits, that's telling me that the diameter of the ball, the biggest it could be is 12. The diameter, okay? So this is telling me that the diameter is 12. If the diameter is 12, what's the radius, guys?
6.
That means the radius would be 6. So the maximum volume of the ball, again, just use the formula. 4/3 pi r cubed. Did anybody already put this in your calculator? What's the answer? 288 pi. Just verify that that's what you get. And finally, the surface area. Again, it's just a formula. 4 pi r squared. 4 pi times 6 squared. Did anybody already do it? That should come out to be 144 pi. All right. We'll have to stop it there. All right, so number 5. Let's see what's going on with number 5. The circumference of the moon is 6,790 miles. What's the surface area? Who remembers how we do this?
1,000,000. Why did y'all get such big numbers?
Well, look at the big number right there.
So big.
Circumference, the circumference formula. I heard Graham say circumference equals pi times diameter. What's the other one? I usually use the other one. That's for area. That's for area. Okay, circumference is 2 pi r. Now, on the formula sheet, I'm only going to give you pi times diameter. If you want to be able to use the 2 pi r, which is very convenient, you're going to have to know that one yourself. Okay, so I'm going to use this. Circumference is 2 pi times the radius. But they gave us the circumference, right? So shouldn't I be able just to take this and substitute it in right here for circumference? Yeah, you definitely have detention there, Austin.
Yes.
Yay, Lucas buddy.
So that's going to be 6,790. Put your phone on your desk now, please.
Well, I got your phone.
6,790 equals 2 pi times the radius. So I should be able to solve this real quick and find the radius. So let's divide both sides by 2 pi. Okay, just put that in your calculator and tell me what you get. Okay, I heard the radius was 1,080.66. Does anybody else agree with that?
I just put 7.
Why?
Go ahead and keep 2 decimals or even more until the very, very end. So that's the radius. Are we done? Do I put a box around that and go to the next problem? No, because what are we supposed to find?
Surface area.
We're supposed to find the surface area. So we're not done yet. What's the formula for surface area? 4 pi r squared. So we're going to go ahead and take this radius and substitute it into the formula. So this is going to become 4 pi times 1,080.66 squared. Okay, go ahead and put that in your calculator. Alright, so this is what we should get for surface area. Any questions on number 5?
No.
Okay, I remember Austin had a question about, had trouble with number 6, so get ready to pay attention. And he wasn't the only one, so everybody pay attention. Here's the formula for the volume of the sphere. Basically, I need to solve this for r. I need to get r by itself. Any ideas? What I'm going to do?
You need to divide by 4/3.
Yes! Here's the problem with that. The suggestion, for people that are listening to this at home, the suggestion was to let's divide both sides by 4/3 pi. Normally, we're going to find like a decimal, and we have numbers and everything, so we could just put it in the calculator, and the calculator would sort it all out. But for this problem, we have all variables. So the calculator won't help us. So we're going to have to do it piece by piece instead of just dividing everything like we normally would. Do you see a denominator in this problem?
3. Yeah, 3.
Yeah, denominator of 3. What do we usually do just to get rid of a denominator? We multiply it by 3, or whatever's in the denominator, in this case 3. So if I were you, that's what I would do first. If you see a denominator and you really are doing it step by step, multiply by the denominator. So if I multiply both sides of this equation by 3, it would be like this here, times 3 times 3. If I multiply this by 3, what happens is we get to cancel out the 3's because we multiply. So now I have so far 3v equals 4 pi r to the 3rd power. That's what I have now.
Divide by 4 pi.
Now I'm going to divide by 4 pi to get r to the 3rd power by itself. Do you see it?
Mm-hmm.
So let's divide both sides by 4 pi. Okay.
If r is cubed, does that mean it's alone, and we have to get rid of the cube?
We got to get rid of the cubed as well. Okay, so we did both sides by 4 pi. That way the 4 pi cancels itself out. And now I have 3v over 4 pi equals r cubed. What's the last step? How do I uncube things?
Square it.
Right. Technically, we will call it the cube root instead of the square root. But I understood what you meant. You were picturing doing this. Making that symbol just like we do for square root with one small adjustment.
3 of them.
Yeah, we put a little 3 here to represent that we're doing the cube root instead of the square root. Alright, so this root will have the effect of canceling out the 3rd power. So that will leave r by itself. So we're ready to write the answer. So that means r is going to equal the rest of it, the cube root of 3v over 4 pi. And that would be the answer. Okay, with that in mind, try to do the next one by yourself. Alright, Shreya, let's do number 7. So, same idea. We're trying to get r by itself. So, this is a lot easier than the last one. Can you give me one step, Brooke? Look back at the last problem. When I had something similar, look at this red right here. When I had 3v equals 4 pi r to the third power, and I wanted to get r to the third power by itself, what did I do?
You just made 4.
Exactly. Now this is almost the same thing. I've got something equals 4 pi, and then I've got this r to this r squared, so what do you think I'm going to do?
Divide it.
4 pi. 4 pi. Yeah. Is this making sense now, Brooke? I'm trying to get this by itself. Just look at what's with it. It's got 4 pi with it, so I want to divide by 4 pi. That way the 4 pi cancels out, and I have r squared equals s over 4 pi. Okay? Braxton, what will I do now, my friend? The root 2. Okay? To get rid of this fact that it's squared, I'm going to definitely take the square root of both sides. So this one is actually simpler than the previous problem. So that's the answer. Yeah, we don't need. It's not wrong, but you're right.
Don't you do that.
Yeah, when the 2 is understood, we shouldn't put the 2. I don't know why. I don't know why I did that.
You're crazy. You're welcome.
Well, there's that. So that's going to be the answer.
The 5 or an S? Oh,
It's an S from the original. Okay, we're going to have to leave it there.
We already started.
Okay, moving on to problem number 8. Now look, there were 2 different types of problems that we used to solve in very similar ways. Remember these formulas? Part over whole equals part over whole. Notice I have it here twice. That's because we used to use these formulas to solve problems that involved arc length and problems that involved sector area. Remember that circumference is the entire distance around the circle. It's exactly like the perimeter of a polygon, except for a circle. That perimeter is called the circumference. And it's given by a formula. Circumference equals 2 pi r. That's 2 pi times the radius. Or, put another way, circumference is pi times diameter. Now this second version is the one that shows up on your formula sheet, but sometimes the 2 pi r version is more convenient, so I suggest that you memorize this version as well. Now when we talk about part over whole, the circumference is the whole that we're talking about. Now when we talk about the part, that is the arc length. Okay, the arc length is just part of the length of a circle. It's basically what you would have if you took a piece of string and laid it along the circle. So think of it as a length. It would be in inches or centimeters, just like a piece of string. So this red illustrates the arc length. So one version of doing part over whole equals part over whole, if we're looking for the arc length will be the part, and the circumference will be the whole. And of course, when we do the circumference, we will do the 2 pi r. On the other side, of the equation, part over whole, we'd be talking about degrees. We'd be talking about the measure of the arc, not inches, but degrees, like 45 degrees or something like that, divided by the total degrees, 360. Now, the other problem that was similar was when we dealt with sector area. Alright, sector area is similar to arc length, but sector area is just like the name implies, it's an area. So instead of just being the border, the edge, a partial edge of the circle, it involves the entire area, sort of like a slice of something, like a slice of pizza. All the space inside of this area is the area of this sector. And so, when we talk about part over whole, when we're looking for the area of a sector, the part is the area of the sector. Of course, the whole is going to be the entire area of the circle. Who remembers how we find the area of the entire circle? Well, if you forgot, you could look at the poster above the board, and you will find that the area of a circle is pi r squared, pi times the radius squared. So again, when we do part over whole equals part over whole, if we're looking for the area of a sector, the part will be the area of a sector, that slice. The whole will be the area of the whole circle, pi r squared. On the right hand side, it's degrees. Just like for arc length, we will still be doing the partial degrees divided by the total degrees of the whole circle. Of course, we know the total degrees in a circle is always 360. Now, with that in mind, let's try to do problem number 8. We need to find the lengths of these arcs. Okay, so let's just take it one at a time. If I want to find the length of arc PR, alright, we're finding lengths. So arc PR is this arc right here that goes like this. Alright, so that's the arc we're looking for. Now, just like we said up there, we're going to do part over whole equals part over whole. Okay, but on the left side, we're going to do part over whole length. Now, the partial length is what we're looking for in this case. So we're just going to call that x. The whole length is the circumference. And remember, the formula for circumference is 2 pi times the radius, which in this case is 10. Now, on the right-hand side, we're going to do part over whole degrees. Now, what are the degrees of this arc? Now, let's be careful. In the past, we've had problems where the central angle was given, and the angle and the arc were the same thing. But in this case, the angle that matches with this arc is an inscribed angle all the way over here on the edge of the circle. So what is the relationship here? So what will be the degrees of this arc? Hopefully you're realizing that when you have an inscribed angle like this, the arc length, not the length, the arc measure, the degrees are double. So the partial degrees will be 140. That's double 70. Okay? Of course, the whole degrees are 360. So you have to keep straight. An arc has two different numbers assigned to it. An arc has a measure in degrees. In this case, this arc is 140 degrees. But an arc also has a length. That's going to be something more like inches or centimeters or something like that. In this case, it's just going to be units, but it's a length. So an arc has both. On the left side, we're finding the length of the arc. On the right side, we're putting the degrees of the arc. So now we can go ahead and solve this. Now I have encouraged you to reduce the fraction on the right first by typing this into your calculator. So let's go ahead and do that now. So that's going to give us 7 over 18 once we reduce this. On this side we have x over, so let's 2 times 10 is 20, so we'll just go ahead and put 20 pi. What do you think I'm going to do now? Somebody in the room probably said cross multiply, and you'd be exactly right. So let's do 18x equals, and let's do 7 times 20. Let's not make a decimal yet. Sometimes they will have us leave the answer in terms of pi. So let's leave pi in the problem for now. 7 times 2 is 14, so 7 times 20 is 140. So that's going to be 140 pi. Just don't forget your pi. And of course, to get x by itself, let's go ahead and divide both sides by 18. So divide by 18, divide by 18. So that's going to give us x equals. Now once again, let's go ahead and reduce this. This is going to be reduced to 70 pi over 9. Now this is the arc length, x, that we were trying to find. So there are two possibilities. Sometimes they ask us to leave our answers in terms of pi. That would mean they would want this for the answer. This is what it means to leave our answers in terms of pi. But sometimes they want a decimal, so we could just use our calculator to get the decimal, which would be 24.43. So be prepared to recognize the answer in either form. Okay, so that's the first arc. So far we have found arc PR, which is 24.43. So I'll just go ahead and mark that. Arc PR was 24.43. Okay, but we're also supposed to find arc RQ, this arc over here. So I'm going to call this one Y. Okay, so let's find arc Y. Now this is going to be pretty much the same thing. We'll just do it all over again. Okay, for this arc, so once again we're going to do part over whole equals part over whole. And the part, this time we're calling it Y. The whole, well, it's the same circle, so the whole will still be the circumference 2 pi r, which turns out to be 20 pi. So we can sort of skip that one step and use the 20 pi from before. We can also use the angle that matches with the arc Y. Should probably change colors. Okay, looking at the 60-degree angle, and now we're trying to find arc Y, which is this arc right here. Okay, if based on the 60 degrees, what is the measure of arc Y? Okay, arc Y is going to be 120 degrees. Again, double. So that's the partial degrees, 120 degrees over 360. Let's go ahead and reduce that. So we're going to have Y over 20 pi equals 1/3. Cross multiplying gives us 3y equals 20 pi. if we divide both sides by 3, okay, then that's basically going to give us the answer. If they want us to leave our answer in terms of pi, it would be 20 pi over 3. If they want a decimal, that turns out to be 20.94. So now we have found the length of our Q, 20.94. Now, if I wanted to find the remaining length of QP, I could do a similar part over whole thing again. First, I'd have to find the remaining angle by subtracting these two from 180, but then I could do the whole thing again. But if I'm slightly more clever than that, which I am, then there's a quicker way to do it. We know the total length of the whole circle, correct? That was called the circumference, and we already calculated it. It's 20 pi. So since we know the whole length of the circle, the circumference, and we just found the red length and the green length, then what would be a quicker way of calculating the remaining blue length? Well, I'm hoping you were just thinking that the length of, let's call this Z. So this remaining length Z, the length of arc QP, will be the whole length minus the two lengths that we just found. So if I do 20 pi minus 24.43 minus 20.94. This will give me the remaining length most quickly. Just put all that in your calculator and see what we get. Okay, this turns out to be 17.46. And that's the remaining length. Okay, that's how you could find all three arc lengths. Okay, let's move on to number 9. We are supposed to find the area of sector QOR. This is part A. So sector QOR, of course. Okay, so QOR is like this, and we're supposed to find the sector, so it will be bounded by this arc over here as well. Okay, so this is the the sector that we're trying to find the area of. Alright, so we do have some information to add to this. We know that the measure of arc QR is 120 degrees. So we know that this is 120 degrees out here. So that's going to be helpful. We also know the radius is 20 centimeters. So we're going to need that too. So the radius is 20 centimeters. Okay, that should be enough for us to find the area of that sector. Okay. So we're going to use the model of part over whole equals part over whole. So part over whole equals part over whole. But in this case, we're talking about partial area divided by the whole area of the circle. So the partial area, well, that's what we're looking for. So I'm going to call that A. I use a lowercase a when I'm talking about a partial area. I like to use an uppercase A when I'm talking about the whole area. But for right now, I won't use an uppercase A because I'm going to go straight to the formula. The whole area is given by pi r squared, right? Okay, remember the whole area of a circle is pi r squared. In this case, that is pi times 20 squared. Okay, so that's my part over whole. Partial area over the whole area, which is pi r squared. Now over here, we do degrees, always degrees. The partial degrees are 120 from right here. Of course, the total degrees are 360. Let's simplify this up a bit. So the partial area over the whole area. 20 squared is 400. So let's go ahead and write this as 400 pi. 120 over 360 reduces to 1/3. Cross multiply. So that's going to give us 3a equals 400 pi. So therefore the partial area, if we divide both sides by 3, is going to be 400 pi over 3. So that is the answer to part A. Okay, the area of this sector is 400 pi over 3. Of course, if they wanted a decimal in the multiple choice, we could find that as well, just by putting it in the calculator. I'll leave you to do that on your own. But let's see what part B says. What is the area of the quadrilateral? Okay, I feel like I need to copy this picture over again. Stand by. Alright, well, we're supposed to find the area of quadrilateral QPRO. QPRO. So, it is this strange shape inside of here that, this is the quadrilateral I need to find the area of. Now, here's the strategy that I would recommend. Of course, we don't know a formula for that strange quadrilateral. But we do know the formula for finding areas of triangles. So I think it will be helpful if we go ahead and split this large shape into two triangles. If we find the area of one triangle, then we can just double it, and that will be the area of the quadrilateral. So that should be our strategy. So let me just write that down. So we're going to go ahead and find the area of one triangle. Okay, well, how are we going to do that? Well, let's see. First of all, we know that this triangle, let's work on the bottom triangle here. We know that this triangle has an angle of 120 degrees. Okay, that was given to us in the problem. So 120 degrees. Well, let me back up for a second. We're not actually told that these angles inside of here are 120. We're told that arc QR is 120, which means this central angle is 120. But we can deduce that these two angles are also 120 because we're told that PQ and PR are congruent. So we know that these are congruent. Because of that, we know that these two angles are congruent. So if we start with 360 degrees and subtract 120, that leaves 240 degrees to be shared equally between these two sides of the circle. And of course, 240 divided by 2 gives you 120. So we can quickly deduce that these angles are 120 degrees. Now, if I may, let me just move this triangle over here, make it a little bigger, so that we can work with it more easily. Okay, will you accept with me that this is, I've copied one of these triangles over to here. So if you accept that with me, then you will accept that this is 120 degrees up here. But now, watch what I want to go ahead and do. Before I even write down the 120, I'm going to need to find the area of this triangle. That's our whole goal, is to find the area of one triangle. And we know that the area of a triangle is 1/2 base times height. So I'm going to need the height. So let's go ahead and do this. There's the height. Now, if the entire angle was 120 degrees, how big will one of these angles be now that I've split it? Well, half of 120 is 60. So this is 60 degrees. Alright, that's going to be really helpful. 60 degrees, that means this is a 30, 60, 90 triangle. So we can use our 30, 60, 90 triangle knowledge. Now remember, we know what the radius of the circle is. Okay, if we look back up there, remember that the radius of the circle is 20. Okay, that means that this top side of the triangle here, this is a radius right here. So this would be that same distance. This because what we're doing is basically we dropped an altitude over here. That's this, and so here's our 90-degree angle would be right here. So this radius, which was 20, is the hypotenuse of the triangle. Okay, the hypotenuse of this triangle is the radius. So that means this is the radius. Alright, I'm just making it bigger, that's all. So that's the radius is 20. Now, in a 30, 60, 90 triangle, if the hypotenuse is 20, what will the short leg be? Across from the 30, that's going to be 10. Short leg is 10. Now, if the short leg is 10, what's going to be the long leg from here to here? Well, that's going to be 10 radical 3. Now, remember, our job is to find the area of this triangle. So that's going to be 1/2 base times height. Now I've got the height, that's 10. But so I need the base. Now the base is this entire distance from here all the way to here. Can you see what it's going to be? How about 20 radical 3? How did I get that? Well, 10 radical 3 is half of the base. So the whole base should be double that, or 20 radical 3. So if I want to find the area is going to be 1/2 base times height, which in this case is 1/2 20 radical 3 times 10. Now, if you type all this in your calculator, it's going to give you a decimal right away. And we don't want that. So the way to avoid getting a decimal right away is just to save the radical 3 and put that off to the side. So in your calculator, you could just do 1/2 times 20 times 10. Now, you should be able to do that in your head. What's half of 20? 10. And then what's 10 times 10? 100. So hopefully you don't really need your calculator to do that. But then we could just take our radical 3 and just stick it on the end. So a lot of times the answers will have the radical still in them. So don't just, you need to know how to get an answer that still has a radical in it, and that's how you do it. Just save the radical off to the side. Now remember, this is the area of one triangle. We are supposed to find the area of the whole quadrilateral, which is made up of two triangles. So, let me just get this out of the way for a second. If I want to find the area of two triangles, I'm just going to double the area that I just found. So area of the quadrilateral that's going to be double the area of one triangle. So that's going to be double the 100 radical 3. So that's going to be 200 radical 3. So that is the area of the quadrilateral. Of course, we could get a decimal now if we needed to. Alright, so we move on to number 10. An equilateral triangle that has 10 centimeter long sides is inscribed in a circle. What's the area of the circle? Well, let's start by drawing a picture. Alright, so here's a circle, and here is an equilateral triangle that is inscribed in that circle. The sides are length 10, so that means 10 and 10 and 10. But we know an equilateral triangle will always have 60-degree angles. So this is 60 and 60 and 60. Again, I know these are all going to be 60 degrees because a triangle has 180 degrees total. 180 divided by 3 is 60. The reason why I'm not drawing this 60 in yet is because I can bet that I'm going to need to divide this triangle up first. So let's do this. Here's the center of the circle. Let's draw 3 radii like this and divide this triangle up into 3 triangles. Okay. Now, my goal is to find the radius of the circle. We're supposed to find the area of the circle. And we know that the area of the circle is pi times the radius squared. So all I need is the radius, and I've got it. So I'm going to use one of these triangles that I've created in order to find the radius of the circle. Now, let's see, watch how I do it. Each one of these 3 angles here at the center are 120 degrees. Okay, so this is 120, and this is 120, and this is also 120. I just did 360 divided by 3. That's where the 120s are coming from. Now, I'm going to go ahead and split. I'm going to work on this bottom triangle. Alright, if I split that one again, okay, drop down in altitude. Now what I have now is, okay, here's a right angle. Now if this whole thing was 120, of course, that means this is going to be 60. So I've got myself a 30, 60, 90 triangle, which is great because I know all about 30, 60, 90 triangles. Now, I can work on that 30, 60, 90 triangle to find the radius. From this part of the triangle right here, okay, how long is that going to be? Alright, clearly that's going to be 5. Since the whole thing is 10, then that's going to be 5. Okay, now, unfortunately for us, this is the long leg. So it's not going to be as nice and neat as I would have liked, because this is the long leg. And the long leg, if we look at our model for 30, 60, 90 triangle, we see that the long leg is x radical 3, where x is the short leg. The long leg is x radical 3. So with that in mind, the long leg is going to be x radical 3. So that means this 5 must equal x radical 3. If I solve this little equation, that's going to give me the short leg, because that's what x represents. So let's go ahead and just divide both sides by radical 3 by doing this. If I put this in my calculator, 5 divided by radical 3, I'm going to get 5 radical 3 over 3. Now that's not very pretty, but that is the length of the short leg. So the short leg is 5 radical 3 over 3. Now let's not lose sight of what we were trying to find. Our goal is to find the radius of the circle so we can find the area. Alright, now if I have the short leg, how do I get the hypotenuse? Well, the hypotenuse is double the short leg. Short leg is x, the hypotenuse is 2x. So the short leg is double. So if I double 5 radical 3, it's basically going to be like doubling the 5. So the hypotenuse, which is the radius, is going to be 10 radical 3 over 3. Okay, now that is very important. We have just found the radius by doubling the short leg. Okay, so we need to take that and put it into our formula. So the area is equal to pi times the radius squared. So that's 10 radical 3 over 3 squared. Let's put the 10 radical 3 over 3 squared into the calculator and see what happens. If you type it into your calculator, it's going to look like this. If I hit enter, it's going to give me this decimal right away, which is fine if the multiple choice answers are decimals. But what if they are not decimals? Sometimes if I hit this button, it will give me an exact answer without the decimals. So 100 over 3 is what I have. So that makes this, the area of my circle is, okay, and I had 100 over 3 was just this part of it, but then I've still got the pi. So that's going to make this 100 pi over 3. And that is the area of the circle. The end.